Imagine descending into the ocean until every trace of sunlight disappears. Then keep going. A few hundred meters become a few thousand. The water turns black, the temperature drops, and the pressure becomes strong enough to destroy machines built specifically to survive it. But then, at the bottom of this darkness, scientists discover something that changes the question entirely. Life is there. Not just a few scattered organisms, but entire ecosystems living without sunlight. And then comes something even stranger. Instruments begin detecting oxygen where photosynthesis should be impossible. NASA has been studying the deepest ocean partly because these places may resemble the hidden oceans of alien worlds. And now scientists are sending new technology back into the darkness to find out what is really happening down there. The ocean covers most of our planet, yet the deeper we go, the less familiar Earth becomes. From the surface, the sea looks like one enormous body of water. But underneath that surface is a vertical world divided into completely different environments. Light disappears, temperatures change, pressure rises relentlessly, mountains, trenches, plains, volcanoes, chemical springs, and entire ecosystems exist where humans cannot survive without machines. The deepest parts are so difficult to reach that, in some ways, exploring them is closer to exploring another planet than exploring our own. The deepest known point in Earth's ocean lies inside the Mariana Trench, at a place known as Challenger Deep. It is nearly 11 kilometers below sea level. If Mount Everest were placed there, its summit would still be covered by water. At that depth, pressure reaches an extraordinary level, roughly 1,000 times the pressure humans experience at the surface. Every square inch of equipment is being pushed by enormous force. A vehicle that survives near the surface can be completely useless there. A tiny structural weakness can become catastrophic. And this is where the story of modern deep ocean exploration becomes almost unbelievable. Scientists did not simply build a submarine, send it down, and start exploring. They had to develop machines capable of surviving crushing of pressure, operating in darkness, navigating without GPS, communicating across kilometers of water, and returning enough information to justify the enormous effort. Even then, success was never guaranteed. In 2014, Woods Hole Oceanographic Institution's deep diving vehicle, Nereus, was exploring the Kermadec Trench in the South Pacific. The mission was part of a scientific expedition designed to study one of the deepest and least understood environments on Earth. Nereus had already demonstrated that robotic technology could reach extreme depths, but on May 10, 2014, contact with the vehicle was lost at roughly 9,190 meters below the surface. Investigators later concluded that the vehicle had likely suffered a catastrophic pressure-related failure, with parts of it imploding under the extreme conditions. The loss was more than a technological failure. It demonstrated just how hostile the deepest ocean can be. At nearly 10 kilometers down, there is no rescue mission waiting nearby. There is no diver who can simply swim toward a damaged machine. There is no easy way to repair equipment at that depth. When a vehicle fails, the ocean can simply take it. But the loss of machines like Nereus also pushed researchers toward a different idea. Instead of relying entirely on large, expensive vehicles controlled from the surface, what if scientists could build smaller autonomous robots capable of thinking and navigating for themselves? What if several machines could work together, map the seafloor, identify interesting areas, collect information, and continue operating without constant human control? That question is where NASA enters the story. At first, NASA seems like the last organization you would expect to be interested in the deepest parts of Earth's ocean. NASA is famous for rockets, spacecraft, Mars rovers, and telescopes. But the agency has another reason to care about environments where humans cannot easily go. Some of the most interesting places in our solar system are not dry planets. They are ocean worlds. Jupiter's moon Europa is covered by a thick layer of ice. But beneath that frozen surface, scientists have strong evidence for a huge saltwater ocean. NASA describes Europa as one of the most promising places in our solar system to investigate environments that could potentially support life. The ocean may contain more liquid water than all of Earth's oceans combined. And because the water is hidden beneath ice, scientists cannot simply land on the surface and look into it. They have to understand how to explore environments that are dark, isolated, chemically complex, and extremely difficult to access. That makes Earth's deep ocean incredibly valuable. The ocean floor gives scientists something that a spacecraft cannot easily provide: a real-world laboratory where they can test machines, navigation systems, sensors, sampling techniques, and autonomous decision-making under extreme conditions. If a robot can learn to move across an unknown seafloor without GPS, identify geological features, and operate independently in darkness, those lessons could eventually become useful for exploring environments far beyond Earth. One of the most fascinating examples is Orpheus, an autonomous underwater vehicle developed through collaboration between Woods Hole Oceanographic Institution and NASA's Jet Propulsion Laboratory. Orpheus was designed to explore extreme depths while using a navigation system based on cameras and visual information rather than relying on conventional GPS. Its system identifies features on the seafloor, such as rocks, shells, and other structures, and uses them to understand its movement and position. The concept is related to terrain relative navigation technologies used in Mars exploration. Think about what that means. A Mars rover can look at the ground beneath it and use visible landmarks to understand where it is, but an underwater robot cannot use GPS signals deep below the ocean. It has to create its own understanding of the terrain. Instead of seeing roads, buildings, or mountains, it may see rocks, ridges, shells, sediment patterns, and other features. The robot can turn those details into a kind of underwater map, and NASA and its partners are pushing this concept even further. A newer vehicle known as Deep Venture has been developed by Woods Hole Oceanographic Institution in collaboration with NASA's Jet Propulsion Laboratory. Unlike a vehicle designed for only a particular depth range, Deep Venture is engineered for full ocean depth operations, down to approximately 11,000 meters, close to the maximum depth of Earth's oceans. It is autonomous, designed to operate with advanced navigation and decision-making systems, and capable of landing on the seafloor, collecting samples, and continuing its mission. This matters because the future of deep ocean exploration may not depend on one giant machine. It could depend on fleets of smaller machines. Imagine dozens of autonomous vehicles descending into different sections of the abyss. One maps the terrain, another searches for unusual chemical signatures, another collects biological samples, another measures temperature and pressure. Together, they could explore areas that would take humans years to investigate. But in the late 20th century, scientists discovered ecosystems around hydrothermal vents that challenged this simple picture. Hydrothermal vents are openings in the seafloor where hot, chemically rich fluids emerge from Earth's interior. Some vent fluids can reach temperatures far above the conditions in which most familiar organisms could survive. Yet around these vents, ecosystems can be astonishingly productive. The secret is not sunlight, it is chemistry. Microorganisms can use chemical compounds as energy sources. Instead of photosynthesis, they rely on processes associated with chemosynthesis and chemoautotrophy. These microbes become the foundation of ecosystems that include animals, such as giant tube worms, clams, shrimp, and other specialized organisms. This discovery changed more than our understanding of the ocean. It changed the way scientists think about life elsewhere. If an ecosystem can exist in complete darkness on Earth, then sunlight cannot be treated as an absolute requirement for life. If organisms can obtain energy from chemical reactions instead of sunlight, then environments hidden beneath ice or buried inside planets become more interesting. Suddenly, an alien ocean does not have to look like Earth. It does not need beaches. It does not need forests. It does not even need sunlight. It may only need water, chemistry, energy, and enough stability for life to persist. That is why hydrothermal vents have become so important in astrobiology. Scientists studying Europa, Enceladus, and other ocean worlds are interested in whether chemical energy could support life beneath layers of ice. The deep ocean provides one of the closest natural laboratories we have for understanding such possibilities. But hydrothermal vents are only one part of the story. Elsewhere on the seafloor, methane and other chemicals escape from sediments through areas known as cold seeps. These environments can also support specialized communities. Instead of relying directly on sunlight, organisms become connected to microbial processes involving chemicals rising from the seafloor. Then there are brine pools. In parts of the deep ocean, extremely salty water can collect on the seafloor and form dense pools that behave almost like underwater lakes. Because the brine is much denser than ordinary seawater, it can remain separated from the surrounding ocean. The edges can become biological hotspots, while the interior of the pool can be hostile to many organisms. Imagine looking across the bottom of the ocean and discovering what appears to be a lake. Except the lake is underwater. There is no shore you can walk onto. There is no surface reflecting sunlight. There's only an extremely dense layer of salty fluid sitting on the seafloor. These environments are reminders that the ocean is not one uniform habitat. It contains thousands of chemical and physical niches, many of which are still poorly understood. And the mystery goes even deeper. Scientists have found microbial life far beneath Earth's surface, inside environments isolated from the familiar world above. Deep underground ecosystems demonstrate that the Earth's biosphere extends far beyond forests, oceans, and soil. Microorganisms can obtain energy from geological and chemical processes in environments where sunlight never reaches. This matters enormously when scientists think about Mars. Mars today is cold, dry, and exposed to radiation. Its surface is a difficult environment for life as we know it. But if life ever existed there, or if some microorganisms remain today, scientists increasingly consider the possibility that the most protected environments may be beneath the surface. The same logic applies to icy moons. The surface may be frozen, the ocean may be hidden, the environment may be completely dark. And yet, beneath the ice, chemical reactions could potentially provide energy. This is the reason the deep ocean is more than an exploration target. It is a rehearsal for exploring places humanity cannot yet reach. And then scientists encountered something that made the deep ocean even more mysterious. In 2024, researchers working in the Clarion-Clipperton zone of the Pacific Ocean reported an unexpected observation. They were studying oxygen in the abyssal seafloor using benthic chambers. Normally, scientists expect oxygen to decrease in these sealed environments because organisms and chemical processes consume it. Instead, in some experiments, oxygen levels increased, not slightly. The published study reported oxygen rising over about 2 days to more than 3 times the background concentration. The researchers associated the phenomenon with seafloor areas containing polymetallic nodules and proposed that electrochemical processes involving those mineral deposits might contribute to oxygen production in darkness. The finding quickly became known as dark oxygen. And the name sounds almost like science fiction. Oxygen, at the bottom of the ocean, where sunlight cannot reach, where ordinary photosynthesis should not be happening. At first, the researchers themselves had to consider whether their instruments could be responsible. Was something wrong with the sensors? Was contamination involved? Was there an unexpected biological process? Was some chemical reaction taking place? The more they investigated, the stranger the result appeared. The researchers focused attention on polymetallic nodules. These are mineral-rich formations that grow extremely slowly on the deep seafloor. They can contain metals such as manganese, nickel, cobalt, and copper, making them economically valuable. Some are roughly potato-sized, although their shapes and sizes vary. The original research reported high electrical potentials on some nodule surfaces and proposed that seawater electrolysis might contribute to the observed oxygen production. But there is a critical distinction here. The study did not establish this mechanism as proven fact. It proposed a hypothesis, and by 2026, that distinction had become extremely important. Scientific scrutiny intensified. Other researchers raised questions about the measurements, experimental setup, interpretation, and whether the observed oxygen could really be produced by the proposed mechanism. The debate became serious enough that in April 2026, Nature Geoscience added an editor's note to the original paper, stating that aspects of the article were subject to concerns being considered by the editors. That means the story has changed. This is no longer simply a story about scientists discovering that rocks make oxygen. It is a story about scientists finding a result that challenged expectations, proposing an explanation, and then having that explanation subjected to intense scientific examination. And that is exactly how science is supposed to work. A surprising result is not automatically a new law of nature. It becomes interesting. Other scientists test it. They question it. They try to reproduce it. They search for alternative explanations. And sometimes the original explanation survives. Sometimes it changes. Sometimes it disappears. In this case, the mystery is still alive. And that is where the latest development becomes especially interesting. In 2026, scientists announced plans for new deep-sea robotic investigations designed to determine what could actually be producing the mysterious oxygen. Nature reported that researchers are preparing fresh efforts to investigate the source of the phenomenon directly on the seafloor. So the bottom of the ocean has become the scene of an experiment that is still unfolding. Scientists are not simply asking whether oxygen exists there. They are asking why. Is the oxygen truly being generated at the seafloor? Is it connected to polymetallic nodules? Is there an electrochemical process? Is there an unknown biological mechanism? Or could some part of the experimental method have produced misleading measurements? Those questions are still being investigated. And until the evidence becomes stronger, the responsible scientific conclusion is not that the rocks are definitely creating oxygen. The responsible conclusion is that an unexpected oxygen signal was reported. A possible mechanism was proposed. Serious concerns have since been raised and new observations are needed. But there is another reason this mystery matters. The same mineral nodules that became part of the dark oxygen story are also at the center of a rapidly growing debate over deep-sea mining. Companies and governments are interested in the metals contained in these deposits because nickel, cobalt, copper, and manganese are important industrial materials. The possibility of extracting them from the ocean floor has attracted enormous attention. But mining the abyss is not like digging a hole on land. The environment is incredibly difficult to access. The organisms living there may grow extremely slowly. The nodules themselves may take millions of years to form. And disturbing the seafloor can create sediment plumes that move beyond the immediate mining track. In 2025, a Nature study examining the long-term impact of a deep-sea mining experiment found that biological effects could remain detectable 4 decades after nodules were removed. Some organisms had begun to recolonize disturbed areas, but communities remained altered and physical changes to the seafloor persisted. Another 2025 Nature Communications study monitored sediment movement during a deep-sea polymetallic nodule collector trial at roughly 4,500 meters depth. Researchers found that a sediment plume generated behind the collector traveled downslope, with bottom currents carrying suspended material over considerable distances. That creates an uncomfortable possibility. And what if the strange environment we are only beginning to understand is also an environment we are preparing to disturb? Scientists do not yet know everything that the abyss does. They do not know every organism that lives there. They do not fully understand every chemical cycle. They do not know exactly how ecosystems recover from large-scale disturbances. And now one controversial study has raised the possibility that the mineral landscape itself could be connected to a previously unrecognized chemical process involving oxygen. If future experiments confirm any part of that connection, the scientific and environmental implications could be enormous. But even if the dark oxygen hypothesis eventually turns out to be wrong, the deep ocean remains extraordinary. Because we already know that life can survive there. We already know that chemical energy can support ecosystems without sunlight. We already know that organisms exist under pressures that would destroy ordinary surface equipment. We already know that Earth's deep ocean contains geological structures that resemble landscapes from another world. And we already know that some of these environments provide useful analogs for the hidden oceans of icy moons. That brings us back to NASA. In October 2024, NASA launched Europa Clipper toward Jupiter aboard a SpaceX Falcon Heavy rocket. The spacecraft is traveling roughly 8 billion miles or 9 billion kilometers to reach the Jupiter system. Its planned arrival is in April 2030, after which it will conduct repeated close flybys of Europa. NASA currently plans 49 Europa flybys as part of the mission. Europa Clipper is not going to land on Europa. It is not going to drill through the ice. It is not going to send a submarine into the ocean. Its mission is different. It will investigate whether Europa has places beneath its surface that could support life. The spacecraft carries 9 scientific instruments, plus a gravity experiment. Together, they will study the moon's ice shell, surface composition, magnetic environment, and other properties that can help scientists understand its hidden ocean and its potential habitability. And there is a fascinating coincidence in the timing. While Europa Clipper is traveling toward an alien ocean, scientists on Earth are developing autonomous underwater vehicles capable of exploring the deepest parts of our own ocean. One is in space, the other is underwater. Both are being designed to investigate environments humans cannot easily enter. Both depend heavily on autonomous systems. Both face extreme communication and navigation challenges. And both are connected to the same enormous scientific question. Can environments hidden from sunlight support life? That question is bigger than NASA. It is one of the central questions of astrobiology, because if life does not require sunlight, then the number of potentially habitable environments in the universe becomes much larger. Imagine a planet orbiting far from its star. Its surface could be frozen, its atmosphere could be hostile, its sunlight could be weak. At first glance, scientists might consider it a poor candidate for life. And if those systems work in Earth's ocean, they could influence how engineers think about future exploration of other ocean worlds. That is the quiet connection between the deepest place on Earth and the outer solar system. The ocean floor is not just a place we want to explore. It is a place where we can practice exploring the impossible. But there is still one mystery that refuses to disappear: the oxygen. If future experiments confirm that oxygen is genuinely being generated in the dark seafloor environment, scientists will have to determine exactly how it happens. If polymetallic nodules are involved, they will need to understand the chemistry and the energy source responsible. If the phenomenon turns out to be an experimental artifact, that will also be important. Because science does not become weaker when an extraordinary claim is disproven. It becomes stronger. A failed hypothesis tells scientists what not to assume. A successful reproduction tells them what to investigate next. Either way, the deep ocean wins. Because the experiment forces scientists to look closer. And in 2026, that investigation is not over. New robotic work is being planned specifically to search for the source of the dark oxygen signal. So the headline is not really that NASA found a terrifying creature. NASA did not discover an underwater monster. The terrifying discovery is something more profound. We still do not fully understand our own planet. We live in a world where the majority of the surface is covered by water, yet huge sections of the seafloor remain difficult to observe directly. There are trenches that humans rarely visit, ecosystems that scientists are still cataloging, chemical processes that remain poorly understood, and environments that behave in ways we did not expect. And the deeper we look, the more the boundary between Earth and an alien world begins to disappear. A hydrothermal vent could almost be mistaken for an alien landscape. A brine pool could look like an underwater lake from another planet. A dark ecosystem powered by chemistry could be exactly the kind of environment scientists imagine beneath an icy crust somewhere in the solar system. And a robot navigating across a black seafloor using technology derived from planetary exploration sounds less like oceanography and more like science fiction. But it is happening. The future of exploration may therefore be stranger than most people realize. The next great discovery about life may not come from a telescope. It may not come from Mars. It may not even come from Europa. It could come from a machine descending into a trench on Earth. A small autonomous robot could detect an unusual chemical signal. NASA is not simply looking down into Earth's ocean, it is also looking outward. Europa Clipper is already traveling toward Jupiter, with its arrival scheduled for April 2030. During the mission, it will investigate Europa's hidden environment and determine whether conditions beneath the ice could be suitable for life. NASA's current mission plan includes an Earth gravity assist in December 2026, before the spacecraft continues toward Jupiter. So while scientists on Earth send robots into the deepest trenches, another NASA machine is traveling through space toward an ocean hidden beneath ice. One expedition goes down, the other goes out, and both are asking the same question. What happens when water, chemistry, energy, and time are given the chance to interact in darkness? We do not know yet, but Earth has already given us a warning. Life is much more difficult to eliminate than we once imagined. It can survive pressure. It can survive darkness. It can survive chemical extremes. It can survive beneath the surface. And in some environments, it can build entire ecosystems without sunlight being the primary source of energy. That does not mean life is everywhere. It means we can no longer assume that the most obvious places are the only places worth searching. Maybe the surface of a planet is not where we should always look. Maybe the most interesting worlds are the ones hiding oceans beneath ice. Maybe the most important organisms are microscopic. Maybe the biggest ecosystems are invisible from above. And maybe some of the answers to the question, are we alone, are hidden not billions of kilometers away, but thousands of meters beneath the water beneath our feet. The bottom of the ocean is therefore not simply the end of the map. It is a beginning. A beginning for new robotics, a beginning for new ideas about biology, a beginning for new theories about how life survives, and possibly one day, a beginning for understanding life beyond Earth. The next time you look at the ocean, remember what is hidden below the surface. The blue water you see is only the entrance. Beneath it are mountains and trenches. Beneath those are ecosystems powered by chemistry. Beneath those are rocks, sediments, and microbial worlds. And somewhere in that darkness, scientists are still searching for explanations to observations that do not yet fit neatly into what we thought we knew. The most fascinating part is that the mystery is not finished. The dark oxygen claim remains under scientific scrutiny. The robots designed to investigate it are becoming more capable. Deep-sea mining is increasing the pressure to understand these ecosystems before they are disturbed. NASA's planetary missions are turning Earth's ocean into a training ground for exploring alien oceans. And Europa Clipper is continuing its long journey toward a moon that may contain a massive ocean hidden beneath ice. So when someone asks, what's really at the bottom of the ocean? The answer is not one creature, it is not one secret, it is an entire world, a world where pressure becomes almost unimaginable, where sunlight disappears, where chemical reactions can power life, where autonomous robots must learn to navigate without GPS, where mineral deposits may hold clues to unexplained chemistry, and where every discovery forces scientists to reconsider what they thought was possible. Maybe that is the terrifying part. The ocean is not empty. It is not dead. It is not simply a dark space waiting for humans to explore it. It is alive. It is active. It is chemically complex, and it may contain environments that are closer to the hidden oceans of Europa than we ever expected. For decades, humanity has looked toward the stars searching for another world. But perhaps we have been missing an important lesson beneath our own planet. Before we send a submarine into an alien ocean, we have to understand the oceans we already have. Before we search for life beneath Europa's ice, we have to understand how life survives beneath Earth's darkness. Before we decide that oxygen means life, we have to understand every process capable of producing it. And before we claim that we understand our planet, we may have to explore the places where sunlight has never reached. That is why the next great ocean discovery could be more important than it looks. A robot disappearing into the abyss. A strange chemical signal, a previously unknown organism, a mineral formation, a pocket of water, a source of energy. Any one of these could change what scientists understand about the limits of life. And if the dark oxygen mystery is eventually solved, the answer could become one more piece of a much larger puzzle. If the oxygen is real and has an unexpected geological source, scientists may have discovered a new piece of Earth's chemistry. If the signal turns out to be an artifact, scientists will have learned something equally valuable about how difficult deep-sea measurements can be. And if future investigations reveal something completely unexpected, then the story will become even bigger. Because that is what the deep ocean keeps doing. It surprises us. It forces us to go back, to measure again, to question assumptions, to build better machines, and to look deeper. NASA may be famous for looking toward Mars and the stars, but some of the most important lessons for those missions may come from a place that is much closer. A place where the sunlight disappears, a place where pressure can crush machines, a place where life survives without the sun, a place where robots inspired by planetary exploration are learning to navigate through darkness, and a place where scientists are still trying to understand a strange oxygen signal that may or may not represent a completely new natural process. The bottom of the ocean is not the end of Earth's story. It may be one of the first chapters in humanity's search for life beyond Earth, because if the universe contains other oceans hidden beneath ice, the creatures living in those oceans may not look like anything we have imagined. They may be microscopic. They may feed on chemistry. They may live near hydrothermal systems. They may survive without sunlight for millions or billions of years. And perhaps the best way to understand them is not to begin with a distant moon. Perhaps we begin here, at the bottom of our own ocean, in the darkness, with a robot. And one question that becomes more difficult every time we explore: what else is down there? And if Earth can hide entire ecosystems beneath kilometers of water, what might be hiding beneath the ice of another world? We do not know, not yet. But the machines are going deeper. The science is getting better. And the ocean is still waiting. Maybe the most terrifying thing NASA found was not something living at the bottom of the ocean. Maybe it was the realization that we have barely begun to understand what our own planet is capable of hiding.